Hi, welcome to complex analysis. In the last session, we derived the Cauchy integral formula and especially Cauchy integral formula with the circular path also. Today we will review that and try to give at least one or two typical applications how to use Cauchy integral formula. Towards the end of last session, I already mentioned the study of or to study the properties of holomorphic functions. Cauchy integral formula will play an important role in future. So we just want to have understand the Cauchy integral formula, its all significance and subtlety, and one or two typical applications. That's what is going to be the theme of today's lecture. So let us start. This must be especially piece missing. Okay. So what did we do? We had U, okay, an open set, and fix a point A in U. Look for an answer that BAR is contained in U, and look at gamma R of t equal to a plus r e power I t 0 less than or less than capital R and 0 less than or equal to t less than or equal to 2 by. Right? Then what did we see? For every z in B A R, okay, we have f of z equal to 1 by 2 pi I integral over gamma r or f of w by w minus z. If you want, I write dw, but usually I will even ignore such things. Okay, notice that. So what did we observe? This is a Cauchy type integral. When we define differentiation and path integral, okay, we looked at this kind of integrals and proved. That is, if I define g of z equal to this 1 by 2 pi is not needed, but let's keep it gamma r by f of w by w minus z. What I know is this g is analytic. On where? On C minus the image of gamma. Right? And what does Cauchy integral formula says? Cauchy integral formula says gz is nothing other than f of z for z in BAR. Therefore, f is analytic on BAR. Right? Therefore, so this leads us to conclude, okay, considering for every a as I vary over a in u, then I find that f is analytic on u itself. This is how we concluded. In case you are wondering what is g of z, so that mod z minus a is greater than r, you know that it is going to be, there is an integral, you understand, we had an integral something like dw by w minus z over gamma r, okay, times this integral f of w by w minus z over gamma r, right? This is what our g is, that this is going to be 0. Sorry, this we found that this is going to be our f of this. Okay, we found f of z equal to this, right? And if z is here, then we know this integral is 0, right? Okay. Anyway, forget. Okay, so now please understand, pause, review, proceed. Okay, PRP. Please revisit Cauchy type integral. Okay, Cauchy type integral. This is in somewhere in path integrals, I think. playlist. Perhaps it's the last one. Okay. Now what we want to do is this. We had already seen, let's recall, if g of z is defined to be f is some continuous function from C to C and gamma is any path not necessarily closed, this is continuous, then g of z we define to be integral over gamma f of w by w minus z for z not in gamma, the trace of gamma. Then we put this is analytic on C minus gamma. We also proved something important. Okay, so what did you do? So I had a gamma and I have a z, and let's look at some r, so that bz to r, okay, is contained in C minus gamma. Then this is bzr, this is your gamma r. Okay, this is 2r and this is just r. Okay, then we found out, okay, on this we had an expression for this, g of z is equal to integral over gamma r of f of w by w minus z, and there we found out this is going to be some cn, okay, z minus, maybe I should take it as z naught, okay, for z in b z naught of r, z minus z naught power n 0 to infinity, where cn's are given by f of w by w minus z to the power n plus 1 dw over gamma r, right? So please, again we need power series. These are the things, unfortunately if you go through the standard course you may not realize. To learn complex analysis, start with power series, understand the facts very well. Now g of z, okay, this equal to this for every z on this open disk. This is a power series, and we know what the power series is. If power series in the powers of z minus z naught, cn's cannot be arbitrary. We know they are nothing other than the nth derivative of g, okay, in factorial. Let me rewrite again, nth derivative of g at z naught by n factorial, right? So there in particular we also, since g is analytic, it's infinitely differentiable, we know what the derivatives are. The nth derivative is given by n factorial times integral of f of w by w minus z naught to the power n plus 1. Okay, this is for every, in fact for every z in this. Okay, yes, okay, so keep this in mind. Okay, therefore we now arrive at Cauchy integral formula for derivatives. So P this is just a review, okay, in case you missed it or you just went through, forgot it. Okay, so now let us say U is an open set and F is holomorphic, okay, and fix an A in U and so that B capital R is contained in U, and choose an R less than R. Alright, and let's look at gamma R of t equal to a plus r e power I t 0 less than or equal to t less than or equal to 2 pi. Then what do we want to conclude? We want to conclude the nth derivative of f at z equal to 1 by 2 pi I and n factorial into gamma r of f of w by w minus z to the power n plus 1 dw. Okay, why this follows? This follows from our what we saw about this. As I said, this is for any z, so even though I wrote this, okay, this is for any z. Okay, You see that? That's why we introduced Cauchy type integral twice with the simplest case. Okay, something like gamma is just an interval on the real line in the complex plane. Okay, then we looked at any path gamma and we proved the result twice. Please go through it. Okay, and we also showed it's analytic. When we said analytic, we also understood what the coefficients are. Okay, if we get a power series, then it is a meaning. So we understood that. Okay, please go through those things. Go back. I hope I started. Yes. Okay, so please make sure that you understand this is called Cauchy integral formula for derivatives. I usually denote by this d for derivatives. Okay, right. The next step we want to do is we want see what you have shown. These are certain remarks. So if I have u and f holomorphic, okay, and you fix an a in u, what is it? Whatever r you give me, so that bar is contained in u, then I have a power series expansion of the type Cn z minus a to the power n. N is from 0 to infinity on any bar, that means 0 less than or less than or capital R. You find that? So what I want to claim is the following: the power series expansion of f is valid on all disks or on the largest disks, open disk contained in U. Do you understand what this means? I can choose R as large as possible, so that as long as BR is contained, then this power series expansion, this is valid on BR. So let me say that a little more clearly. Let R be the supremum of R, so that BAR is contained in U. Alright, and then what I want is then f of z equal to summation Cn z minus a to the power n equal to 0 to infinity for z in BAR. Yes? Right. So if this is contained, first notice that BR is contained in U. Why? Why BR is contained in U? See, suppose this is an open thing, therefore mod z minus a is less than r. Therefore I can choose an r so that this is mod z minus a is less than little r, which is less than capital R. Are you following? Because r is the LUB, right? By assumption, what do I know? That BR is contained in U, therefore I have this expansion. Now what you can think of is Cn's may depend on R. Okay, but we know it does not. Why? Because Cn's are related. Okay, the Cn's we know are nothing other than fn factorial at a by n factorial. Notice that f is going to be analytic. Okay, for every r less than this, little r less than capital R, okay, I have a power series expansion. That means f is analytic, and therefore f is infinitely differentiable. Therefore the nth derivative of f at a is defined. Okay, it has nothing to do with your little r or anything. Do you follow that? Okay, therefore my Cn's are unique. Okay, please understand this. These are the subtle points which are usually not explained in books and by teachers. Please understand. As an immediate corollary, If f from C to C is entire, that means what? Holomorphic on the entire plane, entire complex plane. That's why it's called entire. Alright. Then what is R? R is infinity. You understand? Therefore, okay, therefore F admits F power series expansion F of Z equal to C n Z power n, and for every Z in C, that is the entire domain of U. Okay, power series expansion which is valid on the domain of F, which is namely C. You understand that? Okay, because when I say analytic, what do I know? I know the function can be locally a power series. You follow that? But if F is entire, okay, it is same as saying, okay, an entire function is same as saying it's a power series with radius of convergence infinity. So please understand. Therefore, conclusion: F is entire if and only if F is a power series function with the infinity as the radius of convergence. That is, the disk of convergence is all of C. That is, function whose disk of convergence is C itself. So pause, review, proceed. Yeah. Screen sharing. Okay, good. Okay. Notice that when we did path integrals, okay, I think in the third or fourth lecture, okay, if f1 converges to f uniformly on the path, we said integral f1 over gamma converges integral of f over gamma. As a corollary, we identified the power series, the Parseval identity. See, I'm just repeating so that you know it should become part of you. It's not just a theorem which you learn, you just check, forget it. So you will see how various things are connected so that you will have a mastery over the subject. So what did we do? If f of z equal to something like c n z power n, okay, then we said mod integral of f squared, okay, over 0 to 2 pi is summation mod c n squared. Okay, or whatever the thing. Okay, yeah, where we are seeing mod z equal to 1 if you want. Okay, right, from this we derived Lioville's theorem. Namely, a bounded entire function is a constant. Okay, now what I am going to show is how to prove Lioville's theorem using holomorphic unbounded, then f is a constant. Okay, using Cauchy integral formula we want to prove that. Yeah, so since I want to show it's a constant, okay, then it's enough if I show for every z in C f of z equal to f of 0. Right, now I can use Cauchy integral formula. Okay, so I have C, okay, somewhere. Okay, now choose an R so that this is R, so that mod z is less than R, maybe 2R, but let's not worry about it at present. Okay, right, then I know what is f of z. minus f of 0. Using Cauchy integral formula, it is 1 by 2 pi I integral of f of w by w minus z over gamma r, okay, minus f of 0 is f of w by w minus zz, where gamma r is, as usual, standard parameterization of the circle of radius capital R with the center at origin, right? This, by linearity of the path integral, with this we can write as 1 by 2 pi I of gamma r, okay. So 1 by w minus z minus 1 by w, that is going to be w minus z by w into w minus z. Therefore it's going to be f of w, yeah, z f of w by w into w minus z dw. Yeah. Now what is that I want to show? I want to show mod f of z minus f of z equal to f of 0. Therefore I have to show this is 0. Right? That means I want to estimate this object. That means I want to estimate this object. If I want to estimate, what should I do? Natural, it's a estimate a path integral. That means I have to use ML inequality. Now f is bounded, so assume that mod f of w is less than or equal to m for every w in C. It's bounded on all of C. Therefore, it's bounded on gamma r also by the same constant. Right? Now let's look at the picture. How will I do? What kind of estimates I will have? You have an intuition. If I put a modulus, this is going to be 1 by 2 pi will come. Then I want the length of this, which will be 2 pi r. There is an r above. Right? Right? Now mod f of w will be less than or equal to m. Now I want an estimate for mod this 1 by w. That, see, mod w will be r for w in gamma r. Right? Therefore that will also be r. So this r and this r get cancelled. Right? Now mod z is less than r. So if I try to substitute this inequality here, I will get an r here. Are you following me? Just I want to teach you how to do careful estimate. Not, see, mod z is less than r. Therefore, okay, mod f is less than m, less than or equal to m. Okay, now let's look at r minus mod w minus z. Okay, so I have this. This is my 0. Okay, my w is here and z is here. Okay, do I any kind of estimate here? I don't have, because z can be as near to the circle as necessary. So I may not be able to say this is greater than or equal to something. It need not be bounded away by 0. Do you understand? Z can be here. Z can be still further near. Okay, so I cannot get that estimate. Okay, but what I can do is this. Let us look at mod w. Mod w I can write as mod less than or equal to mod w minus z plus mod z. Right? Therefore, mod w minus z is greater than or equal to mod w minus mod z, which is r minus mod z. Right? Okay. So suppose now I substitute. So what do I have? I have z f of z by w into w minus z. So the m, if I take, okay, since mod z is less than or equal to r, I can take it r and m. Okay, this is the modulus for this, and then this will be again r, and w minus z will be r minus mod z. Okay, then I already had 2 pi r. The length of gamma r will be length of gamma r. This will be 2 pi r into r, okay, by r m r minus mod z. Now do you see there? I don't get anything. There is an r below. This r, letting r tend to infinity may not help me. Do you understand? Okay, pause, review, proceed. So I have to be careful in getting estimate. So what I will do is I will say z f of z and w into w minus z. So I will use, okay, this is less than or equal to, okay, mod z into m and r into r minus mod z. Do you understand this? Yeah. Therefore, modulus f of z minus f of 0 is less than or equal to length of the gamma r times this mod z m by r into r minus mod z. So this r get cancelled. Yeah. So I have 2 pi m, right, and then mod z. Remember z is constant now because I have fixed z by 1 by r minus mod z. So that goes to 0 as r goes to infinity. Remember, this is true, this inequality is true for all r as long as r is greater than mod z, right? Therefore I have got this result. Do you follow this? So hence f of z equal to f of 0 for all z in C. That means f is a constant. Yeah. Before I end the lecture, I would like to caution you against one mistake almost all beginners do. In fact, I have even seen some of the teachers do in a hurry. Not that they don't know, but in a hurry, all of us will make mistake. Even I do. Okay. So I want to caution you against that. Okay, let us do. See, so what does it mean? If I have an entire non-constant entire function, what does it mean? F is from C to C is holomorphic and it's not constant. Then by Lioville's theorem, what do I know? It cannot be bounded, because if it is bounded, it has to be a constant. Therefore, it's not bounded. That's all I can conclude. Okay, please understand this. I will explain that by sharing the screen again. So what does Lioville's theorem say? Says a non-constant entire function, that is holomorphic function all of C, is not bounded. Okay, it does not say f of z goes to infinity as mod z goes to infinity. Remember, z going to mod z is a real number, right? Therefore, for real numbers, you should know what this means. So what is the meaning of this? This means that given any m positive, there is an r positive, so that when mod z is greater than r, implies mod of f of z is greater than m. Okay, it does not say this. Okay, this is a common mistake. Let's give an easy example. Let's look at e power z. Okay, that is exponential function from C to C. Right. Now let's look at it. Z is of the form it, where t is real. Right. Now as mod goes to infinity, okay, what does it mean? That is mod z goes to infinity, right? Z equal to it. But what is the function e power z, which is e power it, but modulus of this is always 1. You understand? So here, even though as I go here, okay, z goes to infinity, or here z goes to infinity, okay, f of z does not go to infinity. Please understand this. Okay. A second proof of Lioville's theorem. So let us look at, so let f be bounded entire function, okay, by m, okay, mod f equal to m, etc. Let us look at f of. Then we know what is f dash of z. F dash of z, we have seen it is comma f of w by w minus z whole squared, and this is over gamma r. So let us assume r greater than mod z. Of course, there is a 2 factorial and 2 pi I, etc. Okay, right. Is it all right? Okay, because this is my cn equal to n factorial. Yeah, this is correct. Okay, now let's look at f dash of z. Suppose if I prove f dash of z is 0 for all z, then f must be constant. It must be locally constant, but c is connected, therefore f is constant. Right? That will follow. But this I know how to estimate. Okay, this is going to be 2 by 2 pi in modulus, okay, into m, and mod w minus z as we did earlier is r minus mod z whole squared. Yeah, into 2 pi r. Yeah, so 2 pi cancels, and therefore I am left with r by some constant times r minus mod z whole squared, which goes to 0 as r goes to infinity. This is true for all r, right? Therefore f is a constant. So I had given already two typical applications. I have given two typical applications how to use Cauchy integral formula, okay, by proving Lioville's theorem by straightforward Cauchy integral formula, and then next Cauchy integral formula for derivatives. We also understood the significance of the power series expansion. Yeah, there is one more thing which I forgot. Let me just finish that also. See, we said, if you remember, when we did analytic function, we looked at f of z equal to 1 by z, z in c star. Then we found out if I fix an a in c star, then when I take r equal to mod a, then I have f of z equal to, okay, cn z minus a to the power n equal to 0 to infinity for z in b a mod a. Okay, so do you see that? Now notice that this is my a, and okay, then the largest thing, largest thing, this is my a, okay, forget this is my a, and okay, the largest thing will be r equal to mod a, okay, so that br is contained in c star. Okay, so as I vary a, I will get a different power series expansion. So what I want to say is a holomorphic function. We saw entire function is same as power series function with radius of convergence r equal to infinity, but a holomorphic function is locally a power series, but need not be a power series on all of the domain of f. See, complex analysis, as I keep saying, is not complex calculus. Oh, I forgot to screen share. Okay, let's go. So let us look at f of z equal to 1 by z, z in c star. Then we saw f of z equal to c and z minus a to the power n equal to 0 to infinity. This is valid on the open disk BA mod a. When we did analytic function, this was example I had given. Notice that r equal to mod a is the largest, such that BAR is contained in c star, right? Okay, so f is represented as a power series only on the disk. Okay, now I want to contrast. When I said entire function, it's a power series function with r equal to infinity. Okay, that means an entire function is represented by a power series on the domain of the function. Whereas when I say holomorphic function, it's a locally a power series, but it need not be a power series. It is represented by a power series on the domain of the function. For example, on C star, 1 by z is holomorphic, but it is not represented by a single power series. Please understand the difference. When one goes through complex analysis, these kind of subtleties are not ever understood, because mostly one deals with a lot of calculations. Okay, the theory, the subtlety, and the significant results are lost. Okay, I hope these things help. My course on complex analysis certainly will be tough, and it will be very different from the standard courses in your colleges or institutions. But believe me, if you go through this, your understanding, mastery over the subject will be far superior. That's guaranteed. Okay, we'll meet again.